Hi and Assalamualaikum. For this video, we will present to you about our digital logic project, which is Network Packet Transmission Monitoring System. Before start, let me introduce our team first. I'm Khairunisa binti Muhammad Azani, working with three others, Arina Sofia binti Hamid, Shara Akila binti Yaakob, and Nurin Ifa binti Ahmad Burhan. Let's start with our background project. Our project aims to implement a secure transmission a number of data packets from one source of computer in Lab 1 to another destination computer in Lab 2. Each lab contains 5 computers. The innovative design requires users to input 4-bit password for access control. The entire circuit is designed and simulated using the Digital Electronics DISC simulator and incorporates combinational circuits, sequential circuits, and advanced features for full functionality.
The problem statement of this case study is during the data transmission, there could be inefficiencies in data transfer, especially when the computer is managing big data. Because there could be a challenge when the computer is managing the flow of the data between the source and the destination. Next, there's also been a challenge when monitoring the packet transmission process to make sure the data is still intact and could arrive to its destination safely. Then the error that happened during the data transmission is could lead to the communication failure, which will fail the process of the data transmission, and the other computer, the destination, couldn't receive the data that they needed. Next, the solution for the problem statement is we need to make sure when monitoring the data packet transmission, the process will run smoothly. So we have three main components in our circuit, which is 4-bit counter, comparator, and clock enabler. So the function of 4-bit counter is to keep track of the number of the data packet that has been transferred. Next, for the comparator, it will compare the number of the packet allowed to be transferred and the data packet that has been transferred so that there will be no duplication of the data. Lastly, we have a clock enabler, which is the main features for the security that the flip-flop will only generate the signals when the requirement of the clock enabler is met.
Next is requirements. Number one, multiplexer. We use one multiplexer in Lab 1, which is to let the users choose which computers to transfer the data packets and separate it from other computers. Number two is demultiplexers. We use two demux, which is in Lab 2, to receive an input from multiplexer in Lab 1 and separates it into multiple output computers in Lab 2. And second demux, we use a display controller, which is it will receive an input from clock enabler and route the data to LEDs. Number three is basic gates. We implement three gates, which is OR gates, to receive input from computers in Lab 1 and Lab 2. Second gate is AND gates. It will take input from OR gates, being part of the clock enabler, and act as the password enabler. Third gate is NOT gates. It used to inverse the comparator's output. For inputs, we use four types of inputs, which is first is input switches. It is to turn on the computers in Lab 1 and Lab 2, serve as preset and clear for D flip-flops, and function as bit selector for mux and demux. Second inputs is clock generators. It acts as the data packets. Third is input push buttons. It acts as switch to trigger the clock enabler. And last is input hex digits. Input hex digits we use for the passwords and comparator. For passwords, and 1, 2, and 4 are used for the users to enter the correct bit required for the passwords. And for the comparator, A3 to A0 represent as 4-bit hexadecimal value input that will be compared to another value. 5 is output displays we use at Lab 1 and Lab 2. It is for display the value to determine the computer success transmits data or receives data. We also use at count-up counter for display the result values of each D flip-flop. 6 is 7 segments displays. It receives a binary coded decimal code from D flip-flop and display the decimal number of that BCD code. 7 is lag emitting diodes. It will receive data input from demux and lead when selected by the demux. 8 comparator. It is to check the matches between hexadecimal's value and the output of the count-up counter. 9 4-bit flip-flop count-up counters. The counter will start or stops counting based on the clock enabler. 10 4-bit decoder. It is to ensure the password entered by the user is correct or not. And lastly is clock enabler. It is to enable user to track the data packet transmission when the data count met the requirements and acts as the clock generator for the flip-flops.
Next, I will be presenting on system implementation. For the first one, multiplexer, Multiplexer allows user to select a computer in Lab 1 to transfer data packets to Lab 2, initiating transmission once the clock signal is generated and the computer is powered on. And the second one is demultiplexer. This circuit uses two demultiplexer. The first one is direct data from the multiplexer to be selected computer in Lab 2, ensuring proper routing. For the second one, connected to the clock enabler, select output channel Q0 or Q1. For Q0, light up the display 1 LEDs, while Q1 lights up the display 2 LEDs. And then the third one is basic gate. The circuit uses two OR gates, three AND gates, and one NOT gate. The OR gates detect active computer in Lab 1 and Lab 2, sending the result to the first AND gate. First AND gate check activity in both lab for the clock enabler, and then the second AND gate validates password inputs, while the third AND gate generate a clock signal when all input are high, enabling the flip-flop. The NOT gate inverts the comparator output to control subsystem. And then the fourth one is 7-segment display. The display converts BCD value from D flip-flop output into decimal number and hexadecimal letter, offering a clear visual representation of the data. The fifth one is LED. The LED in the system act as output indicator, lighting up when a specific output of the demultiplexer is activated. Next, inputs. Inputs in the system serve several functions. Switches powers on computer in Lab 1 and Lab 2, control D flip-flop, and determine the output logic S2, S1, and S0 for the multiplexer and demultiplexer. Clock generator in Lab 1 signal data transmission and synchronize data routing in the demultiplexer. The input push button triggers the clock enabler for data transmission, while hex digits N1, N2, N3, and N4 allow user to select input for the password and compare with the counter input. Next, output display. There are 5 output display in Lab 1, 5 in Lab 2, and 4 in the count-out counter. In Lab 1, the display show data packet transfer to Lab 2, while in Lab 2, they indicate the successful reception from the Lab 1. Each display is linked to a specific computer. For the count-out counter, the display shows the value 0 or 1 of each D flip-flop, tracking the counter progress in real time. For the comparator, compares the 4-bit hex input with the count-out counter value and the store password, outputting the high if they match and low if they do not. Next, for the decoder, the 4-bit decoder generates password for the clock enabler. It receives input from the hex digit input and is connected to an AND gates. If the wrong password is entered, the LED stays off and clock remains disabled. When the correct password is entered, the LED lights up, activating the clock to track packet transmission. And then the next one is clock enabler. The clock enabler uses a 4-input AND gate. It is activated when 4 conditions are met. The computer are switched on, the counter computer is true, the correct password is entered, and the clock TRS is clicked. When all inputs are high, the clock is enabled and generated. And the last one is the 4-bit D flip-flop counter increments its binary value with each clock pass, determines state transition. It starts counting when it receives high input from the clock enabler, preset switch, and the clear switch. If the preset switch is high and the clear switch is low, the transmission is set. If the preset switch is low and the clear switch is high, the transmission is reset. If both switches are low, no changes occur. So that's all from me.
We'll be presenting about the implementation of our system. First, I will be talking about the instruction manual. So this is a circuit designed by Group 3 for SACR 1013 Section 3. The component that we use is basic gates, flip-flops, mux comparator, and also decoder. This is the user manual. First, we need to power on the computers, and then we need to fulfill the clock enable conditions. So we have 4 conditions. We need to power on the selected computer, and then we need to set the maximum packet transfer, and then we need to enter the correct password, and then we need to click the clock TRX, which is our push up button. So now I will be giving you guys a tour of our circuit design. So first we have our lab. This is lab 1 and this is lab 2. In both labs you have 5 computers, and this is the clock generator, which represents the data packet, and then this is the turn on power for our computer, and then this is also the turn on power for
the computer in lab 2. Okay. So we use mux and demux here so that we can pick which one of the computer that we want to use, and then it will be transferring to the other computer here. Okay. So down here we have the password component. We use 4-bit decoder for our password. So the password that we have prepared is A75F. So the user need to enter this password so that the clock can be used. Next to the password component, we have the count up counter. So this is the place where we can monitor the data packet transmission. So we use the positive edge triggered flip-flop here. So we have 4 flip-flop because we use 4-bit component. Okay. And down here we have the comparator component. So basically the comparator where we can compare the maximum packet transfer, the maximum data packet that we want to transfer with the data packet that has been transferred. And then next, here we have the fun display that we prepared so that whenever the clock enabler is working, the LED light here will light up. And then next, here we have the clock enabler. So basically, if all of the condition is true, is high, the LED here will light up. And then next, here we have the clock access push up button. So basically, whenever the user push this button, it will transfer the value so the clock can be working. Okay, so now we can test our circuit. So we can start. Okay, so for example, we use this computer. So we need to enable this clock animation. So we can see here the data packet is basically being transferred right now from this computer. So we can choose which computer here. We choose this one, and then we click this. So 010 because this is basically the second computer in lab 2. So we can see here the data packet is being transferred right now to this computer. Now we can set the password A75F. You can see the LED has light up because the password is correct, and we can also set one here. Then we can set the maximum data packet. We can maybe use 8 only. So now we can test our clock. We need to push this button 1. So as you guys can see, the data packet that has been transferred is 1 right now. And then we click again 2, 3, 4, 6, 7, 8. Okay, so as you guys can see right now, if we click this button, the value will not change anymore because we have already reached the maximum packet transfer right now, 8. So although we push many times, it will not move, it will not change anymore because we have already reached the maximum amount. As you guys can see here also, the LED is not turned on anymore because we have reached the maximum amount of packet transfer. So that is all for our DITS implementation. Thank you.
Lastly, the reflection from this project is, as a team, we need to have a strong understanding of digital logic and practical application, especially when handling the content of the project and when using DITS simulator. Next, we need to enhance our problem-solving skills and encourage a creative thinking. Lastly, it is to emphasize effective teamwork and skill sharing among members so that the distribution of tasks will occur fairly. So for the project outcome, we are glad that we achieved and secure data transmission, real-time monitoring, and predefined objective, which have become a success for us in completing this project. Next, we also overcome challenges like debugging and component synchronization. Moreover, for the future improvement, we are agreed that we want to add multi-factor authentication for enhanced security. Next, to expand the circuit to support more device and a larger network for it to handle a big data. Lastly is to integrate a real-time data analytic for improved monitoring and performance. So there will be less error during the data transmission. So that's the end of our presentation. Thank you for your attention.